I'm going to be talking about the sine and cosine function graphs. Okay? So give me a minute to draw the graphs of those functions. Now, while I'm drawing the graphs of the sine and cosine functions, let me mention that I'm going to be using the terms amplitude, period, and phase. If you're not familiar with those terms, I would invite you to watch my video that introduces the graphs of trigonometric functions. There I discuss those terms. All right? So the sine and cosine functions are what's called periodic. So that means that you can interpret them as being formed from a certain portion of a graph that's copied over and over again. Alright, so let me just finish my sketch. All right, so the blue curve is a sketch of the graph of the sine function. The purple curve is a sketch of the graph of the cosine function. All right. Now, you can learn a lot of things from these graphs. Notice that the y values are constrained to lie only between the y values -1 and 1. So that tells us that the range of the sine and cosine functions is the y values between -1 and 1. So I can express that this way. Okay? Now, the x values, it includes all x values because the graphs extend indefinitely to the right and to the left. So because of that, we say that the domain includes all values. Okay? So all values of x are allowed. All right, so you can get the domain and the range from the graphs, certainly. Okay? Now, also, notice that we can determine that the amplitude is 1 for both graphs. So I'll write a equals 1 to denote that. All right? And the period is 2 pi. So I'll write t equals 2 pi to denote that. And then finally, notice that the sine and cosine functions are the same except that each one is shifted horizontally with respect to the other. Okay? So we could say that the phase shift with respect to these two graphs is pi over 2. Okay? Now, specifically, if we shift the sine graph, in other words, if we shift the blue curve to the left by pi over 2, then the blue curve will sit right on top of the purple curve of the cosine graph. So we can say that we can state an identity because of that. We can say that the cosine function is equal to the sine function with the following transformation applied. Okay, so adding pi over 2 to the argument of the sine function turns it into, or makes it correspond to the cosine function. That's because adding pi over 2 that way is equivalent to shifting the curve to the left by pi over 2. All right? Now, I would like to discuss related graphs involving other transformations. Okay? So, what would the graph of 3 sine of x look like? Okay? So, using the information from the previous sketches and knowing what the amplitude and the period of the sine function graph, what those are, you can hopefully see that the graph is going to be stretched in the vertical direction. That's the effect of the multiplying the sine function by 3. Okay, so it'll still have the same shape, but the amplitude is going to be different. Okay, so the amplitude is going to be 3. So if you were to graph it, you'd have to make sure that the biggest y value was 3 and the smallest y value was -3. Okay? Now, if this is confusing to you, I would invite you to watch my video on function transformations. Okay? Let's do another one. What would the graph of the sine of 3x look like? Okay? So, you hopefully know that multiplying the x by 3, the effect of multiplying the argument, the x value, by a number, the effect is that it either causes a stretching or compression in the horizontal direction. Okay, in this case, it's a compression. Okay, so the x-intercepts are going to be different than for just the plain old sine of x graph. Okay, so one way to see where the x-intercepts are is the following. So we know that for the sine function to be equal to 0, the argument has to be 0, pi, minus pi, 2 pi, minus 2 pi, some integer multiplied by pi. So for example, if 3x was equal to pi, then that would give a intercept, an x-intercept. So that occurs at pi over 3. Okay, so the first intercept has to be pi over 3, and then the other one has to be 2 pi over 3. And likewise, on the other side, we have minus pi over 3 and minus 2 pi over 3. Okay? Now, what is the period of this new function? Can you see that the period is 2 pi over 3? Okay? In general, you will notice, and I invite you to investigate further, that you'll notice that if you graph the sine of kx for some number k, you'll notice that the period will turn out to be 2 pi over k. Okay? So, convince yourself that that is true. That'll be helpful to remember. Okay? Now, actually, I take that back. You could memorize it. However, if you can just quickly sketch and use the reasoning that I showed you, you don't have to actually memorize it. You can just quickly derive it. Okay? And then one more example regarding sine. The sine of x plus 3. Let me put the 3 on the left side. Okay? So what would that graph look like? So the effect of adding 3 to a function like that is to shift the graph vertically. All right, so the amplitude and the period, all of that is still the same. It's just that what we call the center line has changed. All right, so something like the following sketch. Now, notice that, again, notice that the amplitude is still 1. It's just that the graph's been shifted. The center line is not the x-axis. The center line now is the line with respect to y equal to 3. Okay? Now, I would like you to do a few exercises. So, can you draw the graph and can you determine the amplitude of 8 cosine of x? So pause the video and do that now, please. Okay, so I'll go ahead and work it out as well. So the amplitude is 8, and the effect of the 8 is to stretch the graph vertically. So a sketch would look something like this, where the graph had a y-intercept of 8 instead of 1. All right? Now, would you please sketch the graph of the cosine of 8x and identify the period if you can. So pause the video and do that now, please. Okay, so I'll go ahead and work it out. So if you were to do an analysis similar to what I did with regards to the sine function, you would notice that the period is 2 pi, for this function, 2 pi divided by 8, or pi over 4. Okay? And so the amplitude is going to be the same amplitude as for the regular cosine of x, so 1. Okay, and one way to see where the x-intercepts are is, well, you could use the period information, of course. So the y-intercept is 1, so it will be, the y value will be 1 again at pi over 4 because of what the period is. Okay. Another way you can work out points is by the following reasoning. We know that if the cosine of, if you're finding the cosine of an angle, if that angle is pi over 2, we know that the cosine is 0. So set 8x equal to pi over 2, so x is equal to pi over 16. So that means that the first x-intercept is at pi over 16. Okay, and the next x-intercept occurs where 8x is equal to 3 pi over 2. So x is equal to 3 pi over 16. Okay, and so that's another way that you could make sure you get the intercepts correct for your graph. And then, of course, here you would have pi over 8 for the minimum. All right, and then on the other side, minus pi over 16. And then the valley, or the minimum, occurs at minus pi over 8. And then that x-intercept is at minus 3 pi over 1/6. All right, so now I'd like you to sketch the graph of 8 plus the cosine of x. So pause the video and do that now, please, if you like. Okay, so I'll go ahead and work it out. So the amplitude will be 1, just like for regular old cosine of x. And the period will be 2 pi, just like for the regular old cosine of x. What will be different is that it'll be shifted vertically. So the center line will be with respect to y equal to 8. Okay, so something like that.